Welcome to another lecture of CS203, the course on probability theory. Today we are going to talk about an entirely new topic called random variables. We have studied a few topics before. We started with the basics of the probability theory and spent our first week on the lectures here. Then we moved on to something called conditional probability. This might have been a slightly new topic to you, but you remember that if A and B are events, in this case, we are interested in probability of A given B or probability of B given A, and we learned Bayes theorems, etc. Today, we are going to have a fresh start. As mentioned before, we are going to talk about random variables. Before we start, what is the motivation? Remember, for a probability experiment, the most important thing is sample space. What was sample space? It was the set of all outcomes. In other words, it could be any set. It could be a set of colors. It could be a set of persons, or even it could be a set of numbers or a set of sequences. In other words, the elements inside the set do not have any meaning. They are just labels. But in most of these cases, we want to associate a number with every outcome. Remember, omega was the set of outcomes, and in many of these situations, we want to associate a numerical quantity with every possible outcome in omega. This is what we want to do. And then, mostly, the task is estimate this numerical quantity. How big or small it is supposed to be in expectation. Let me give you an example. When you buy a lottery ticket, the numerical quantity associated with every outcome is the payment of the lottery. You might win a big prize, you might win a small prize, you might not win at all. So for every outcome, payment of lottery is associated with it. Another example could be when you toss a coin, let's say 10 times, number of heads in the sequence. So you see that there is a numerical quantity, number of heads, with every sequence of heads and tails. In this case, let's say, what do we want to estimate? For example, in the case of payment of lottery, you might want to ask, how much am I supposed to win given probabilities of certain outcomes, right? And that is what I mean by estimating the numerical quantity. So you might have the probability of, let's say, 1 by 4 of winning a big prize, 1 by 2 of winning a small prize, and let's say 1 by 4 of winning nothing. Then you would like to know that if you buy the ticket many number of times, how much will you get, or what do you expect to get if you buy a lottery ticket? To answer such questions, we define the notion of random variables. Now I will give you a formal definition. A random variable is a function from the sample space to real numbers. So it's basically putting in words what we said before. Every outcome is associated with a real number. It is a function and it is called a random variable. Before I move on with some examples, I would like to note that in some literatures and in some applications, the random variable will be defined from omega to any set. This need not be real numbers. We will, in this course at least, we will mostly see random variables where the range is reals. So when the range is reals, such random variables are called real valued random variables. In this course, real valued random variables will be synonymous with the concept of random variables. We will treat them as same. If not, I will mention it clearly that now we are looking at random variables which are not real valued random variables. So unless mentioned, random variables means real valued random variables. Let's take an example of a random variable. Suppose we toss an unbiased coin twice and we are interested in counting the number of heads. So we have a biased coin, we have an unbiased coin in our hand and we are interested in counting the number of heads. What random variable should we define? Let's start with the basic. Basic is the sample space. We have done it before. Sample space in this case is the set which contains 4 elements. So if I want to define a random variable here, it should have values for each of the elements of the omega. And if you want to count the number of heads, then my function will be x of hh will be 2, x of th will be 1, x of ht will be 1, and x of tt will be equal to 1. This is the first example of random variables in your case. In general, as soon as you have an omega, a random variable, and say a sigma algebra, let's assume that our sigma algebra is complete in the sense that it has all possible subsets of the sample space. This is the easy case. In these cases, it's natural to define an event which we call x is equal to x, where small x is a real number. What do I mean by this? This event is the set of all omega, all elements of sample space, such that their value gives me x. I can define this event to be equal to a subset of omega, which is an event, looks like this. Clearly, if I want to write probability of x equal to x, probability of this event, it will be the summation over the probability of all the elements which are contained in this sample space. This is the formula for the probability of these events. Let's take an example and define such a probability distribution function over the random variable. Again, we will take our favorite experiment, toss a fair coin 10 times. And then we want to count the number of heads. It's a similar example, but we are now tossing the coin 10 times. In this case, omega will be all sequences of h comma t of length 10. This we have seen many a times. It should not be a problem. And x of omega should be the number of heads. You can clearly define this function also. And then if someone asks you what is the probability that x is equal to k, then you have to sum up over all sequences where there are k number of heads, their probability. So summation over omega such that number of heads in omega is 10, and I want to sum up over this probability. You can notice that there are 10 choose k many such sequences. For every sequence, the probability is the same. What is the probability? It is half to the power k, half to the power 10 minus k. The coin was fair. This is equal to 10 choose k, half to the power